I have Ning Bao, who will be speaking about applications of the Holevo information to holography.
Okay, thank you very much for the opportunity to speak here. So far the talks have been pretty interesting. Yeah, so like Carl said, today my talk will be on applications of the Holevo information to holography. This is joint work that's now on the archive and going through the editorial process with Hiroshi Oguri, a professor at Caltech. And you can find it with archive number 17 this. Okay, so I guess the motivation of the talk is that in black hole physics, in holography, the concept of distinguishability is an important concept. Why do I say this? Well, let's consider an example. Let's take a look at a black hole, because that's all quantum gravity people seem to want to do. So we have a black hole, and when you have a black hole, you have an argument that the entanglement entropy, or the thermodynamic entropy of the black hole, is equal to the area of the black hole over 4G. So this is something called the Bekenstein-Hawking bound. I guess in this case it's the Bekenstein-Hawking formula. So it's also called SBH, which confusingly, but maybe not confusingly, can refer to either black hole or Bekenstein-Hawking. Right. So the reason why this formula is true is because classically black holes do not radiate. So if you, in a classical solution of GR, the black hole, if you throw anything in it, it goes in and it never comes out. But if you have like a sink like that that exists in a theory, your theory is not thermodynamically, doesn't make sense thermodynamically. So what this means is that quantum corrected black holes need to radiate. This is the, this radiation is what you may have heard other people talk about as the Hawking radiation. And in order for the Hawking radiation to make the theory make sense thermodynamically, you can show that the amount of Hawking radiation, that the thermodynamic entropy of the black hole needs to be equal to this quantity. So that's all well and good, but that's a very, if you will, top-down derivation of why the thermodynamic entropy needs to be this number. Because if you remember, in statistical mechanics, your entropy is related to some log of the partition function. And if you think about it from that context, even if you have this number, it begs the question of what is the partition function and how do you determine the individual terms that comprise your ensemble microscopically. So this question actually ends up being, in the black hole context, something called microstate counting. Which means nothing more than how do you identify the individual terms that comprise the mixed state that is the black hole. How do you identify each individual microstate thereof and then count them and then take the log of them and conclude that the total number of microstates is given by the Bekenstein-Hawking entropy. So this is something that people have successfully done in a very small number of cases. So in particular, Strominger and Waffe they've done microstate counting for extremal black holes, extremal supersymmetric black holes, where they utilize, I guess, the greatly enhanced symmetry in order to show that they can, in that case, count the microstates explicitly and recover this answer. But as far as we know, based on LHC data and other things, we don't yet know if supersymmetry natively exists in our particular vacuum, particularly at low energy. So the question of how one counts microstates for Schwarzschild black holes, for black holes that are not spinning, are not charged, and are not supersymmetric, is actually still an open question. So because of this, the question of distinguishability is a question that's of interest in high energy physics. Because if I can distinguish pairs of microstates from each other, then I can label the microstates that I have access to, and I can simply count the number of distinct labels that I have to determine the number of microstates that actually correspond to a specific black hole.
Do you mean distinguishability in practice or distinguishability principle?
I think you'll see what I mean, but if you don't understand in 15 minutes or so, ask again. Okay, so we can ask, if we're interested in distinguishability, is there anything that information theory gives us that allows us to say something interesting? And there is, and it's this set of literature concerning the Holevo information. So if one is interested in talking about the Holevo information, the best way to define it is to consider a game. So let's say that in this game, Alice and Bob, because it's always Alice and Bob, both share knowledge of the following thing. They both share a matrix of some overall density matrix rho, which can be written as a sum over weighted probability distributions of microstates, or of smaller reduced density matrices. So in particular, Alice and Bob both know what rho is. They both know what each of the pi are, and they both know what each of the individual rho I are. So that's the shared information that both of them start with. So all of the things that appear here are shared. Then what happens is Alice selects an individual of a specific rho x, which is just one of these particular rho i's from the ensemble. And she does not tell Bob which one she chose, but she just picks the specific thing and then gives it to Bob. So after she does that, then it's Bob's mission to determine which one he was given, to essentially to determine what the value of x is. And so he can perform a measurement on rho x, and then based on that, the question is, how much information about the specific value of x can he infer from the measurement that he made? So let's say that Bob makes a measurement and that yields some outcome y. So the Holevo information is, we're not quite at the Holevo information yet. So we can talk about the quantity, the mutual information between x and y, where what this means is, given your knowledge of the value y, this is not quite standard notation, but this is what they use in Holevo information. When they talk, given your knowledge of the value y, what can you infer about the identity of x? Right? So this tells you how much information you can gain about x, given your knowledge of a specific value y. Now, something called the accessible information is defined by taking the supremum over all possible measurement choices that Bob could have made. So in some sense, if he does the best possible measurement over the density matrix rho x he's given, this will tell you the maximum amount of information that he can gain about the identity of x. So this is called the accessible information. I think it's a one-shot statement, because in particular, if it were an asymptotic statement, you would just do full state tomography over rho, and this would always be perfectly distinguishable. So it's a one-shot statement. Yeah. So this is called the accessible information, and it was proven by Alexander Holevo that this is always less than or equal to the Holevo information, which is called chi, which is defined as the entanglement entropy of rho, the full rho, minus the weighted average of the entanglement entropies of the rho I. So I'll write that equation again here because it's important to the remainder of the discussion. This is less than or equal to S of rho minus the sum of pi S of rho I. And this is the Holevo information chi. Okay, so the Holevo information also obeys another property. Not only is it lower bounded by the accessible information, it's also upper bounded by the Shannon entropy. At this point, in particular, this should look familiar to Brian because this is, I got you to look up. This is related to your work with Ahmed and Shi, where you guys were studying the linearity of holographic entanglement entropy. And so in particular, if I just do some rearrangements and enforce that this is an equality, you in particular get that S of rho is equal to the weighted sum S of rho I, what you call the linear piece of the entanglement entropy, minus the Shannon entropy piece, which in your language you called the entropy of mixing. So this follows when this inequality is saturated, which naturally, again, begs the question of when do these particular inequalities get saturated? So it turns out that there are bijective conditions for their saturation. This is saturated if and only if the commutator of rho I and rho j is equal to 0 for all I and j. And this is saturated if and only if rho I and rho j have orthogonal support for all I and j. So in particular, in the cases that you guys were looking at, where you were looking at mixtures over classical geometries, the individual classical geometries themselves, there's a very strong argument that they have orthogonal support relative to each other. So this should be an equality, which is why when you did the heavy-duty conformal bootstrap calculation, you ended up getting a result like this. So this is the particular case when if you're looking at mixtures over classical geometries that have orthogonal support relative to each other, why the specific nonlinearity of holographic entanglement entropy appears in this specific way. Okay. What else did I want to say? Okay, so now that I've defined the Holevo information and some properties thereof, we can talk about how this can specifically be related to the question of black hole distinguishability. So the question of black hole distinguishability, if we're trying to apply that, just requires some definitions. So for this rho, we're going to call this the full black hole mixed state. So, yeah, rho I from rho j. Yeah, that's right. Right. So rho is equal to this. The individual rho I are equal to individual black hole microstates. And interestingly, well, perhaps obviously, the sum of pi log pi, the Shannon entropy from before, this has an interpretation in black hole thermodynamics based on this thing that I was saying before. So this, because is just the Bekenstein-Hawking entropy. Because remember, the Bekenstein-Hawking entropy is defined as some sort of Shannon entropy over the set of all black hole microstates. So these are the definitions that will be relevant when we're talking about black hole distinguishability. So now in this case, we can consider what happens to this equation, but perhaps before we do that, we should consider this in the context of the toy model that everyone's been talking about, in particular the ADS-CFT correspondence. Because the ADS-CFT correspondence allows us to calculate entanglement entropies in terms of geometric quantities, so things that we understand. So just to remind you, the relevant part of the ADS-CFT formalism is the entanglement entropy of some segment L sub A is going to be equal to the area subtended in the bulk, the area in the bulk that subtends L sub A over 4G. Right? So this is the Ryu-Takayanagi formula up to a homology constant. What does this mean? This means that this is my space-time. Remember that if ADS-CFT in general, an empty ADS space can be defined as a soup can, where the can is dual to the soup. ADS-CFT where the bulk has a black hole in it is something like the duality between like a soup can with like a block of ice in the middle of it. That's where the black hole is, and the can. So one can put the black hole in by hand in the ADS-CFT correspondence. So if I have some boundary interval that's like this, that's, you know, smaller than half the size of the entire boundary, then the area that subtends it is just some minimal geodesic in three-dimensional gravity, for simplicity, that goes like this, and it doesn't cross the black hole area. But you can imagine that if I change this, and if I look at an interval size that's larger, say this interval, then what the homology condition tells you is that you need something that can relax continuously to the boundary. So that means that when there's an obstacle, like the black hole in the way, the homology condition tells you that the geodesic that you're considering needs to wrap around the black hole in some way. You can't just flip to the shorter geodesic that goes around this way when there's a mixed state black hole in your bulk. That's what the homology condition means. Yeah. I mean that it will not simply be this piece. Right. Okay. So now that I've defined that, now we can just look at what the Holevo information is. So we have S of rho minus the sum over pi S of rho I. So because this rho is the full black hole mixed state, here I'm promoting it from the full black hole mixed state to the state of the black hole plus the state of the gravitational state around it. So we can talk about it as if it is the entanglement entropy of the entire conformal field theory. Because remember, there's a one-to-one duality. Remember that the state of the boundary is equal to the state of the bulk. So that means that the entanglement properties are the same. So S of rho, because of this homology condition, it's not zero. Because if I'm talking about the entire bulk, then if I imagine taking some finite sized interval and increasing that until it's the size of the entire bulk, the fact that the black hole remains as an obstacle means that I need to retain a piece that circles the black hole. So this will actually end up just being the Bekenstein-Hawking entropy. And this, each of the S of rho i's, because they're black hole microstates, for detailed reasons, are pure states, and the entanglement entropy of any pure state by construction is zero. You can also see this from the Ryu-Takayanagi formula, because when you have a pure state, that essentially means that the black hole is no longer treated as an obstacle from the perspective of the Ryu-Takayanagi formula. So the homology condition goes away, and the minimal geodesic length that subtends the entire boundary if there's no obstacle in the bulk is of zero size. You just don't draw a geodesic. So this term becomes zero. So the Holevo information just becomes the Bekenstein-Hawking entropy. Now, why is this interesting? It's interesting because this equality, I told you that there is a bijective condition for when this inequality becomes an equality. Which means that if the Holevo information is ever equal to the Shannon entropy, which in this case is equal to the Bekenstein-Hawking entropy, that means that all of the rho I and rho j have orthogonal support relative to each other. And as soon as things have orthogonal support relative to each other, then I immediately know how to distinguish them from a theoretical perspective. All I do is I simultaneously diagonalize the overall state rho in the support basis of the individual rho i's, and then I perform a projective measurement to determine which of them they are. And so given any individual rho x, I can not only distinguish a specific microstate, I can distinguish any microstate that I'm given perfectly. So when this inequality is saturated is also known, it's also when you can have perfect distinguishability with Holevo information. When this inequality is saturated, just to go back and complete the picture, what this means is that via a measurement, you can achieve a distinguishability that it's equal to the Holevo information, but that the Holevo information may not allow you perfect distinguishability. So for historical reasons, I believe this is called the point of optimal distinguishability, and this is called the point of perfect distinguishability. Right. So you might think, okay, well, big deal. This isn't very interesting. If you're taking a look at ADS-CFT and you don't even consider the Ryu-Takayanagi surfaces, you just consider the cases where the piece that isn't wrapping the black hole is equal to zero, then maybe you're not doing anything that interesting. Well, one thing that you can do, we'll just erase. is to consider the case of what happens if you don't have access to the entire conformal field theory boundary. In other words, what if the row that you have access to is not the thing that corresponds to the entirety of the black hole plus the entirety of the interior bulk geometry, but rather only some portion of it? Yeah.
So for example, here if rho is in a thermal state, then you could just measure the energy.
Yeah, that's right.
That's what you're saying. And that's the measurement. That tells you which energy eigenstate you got.
Yeah, so in some sense, this part may be not so surprising. The thing that may be surprising to you in particular is what fraction of the boundary you actually need access to before you can attain perfect distinguishability. Okay, so now let's consider again this case where we have some black hole. But now let's not give you access to the entire boundary. Now let's say you have access to the reduced density matrix, for example, that's defined on this particular region. Can you distinguish the various black hole microstates from each other? Well, here, now it's a little bit non-trivial because here, the S of rho's, in this case, S of rho is not equal to 0 in every single case because now, it's not equal to the Bekenstein-Hawking entropy. So that makes things more complicated. And furthermore, S of rho I, because now you've traced out a system, so even in a pure microstate, if I've traced out a portion of it, it's no longer a pure state. Now this is no longer 0. So you no longer have quite as simple of a situation as you do here. But we still have a situation in which the entropies are defined by geometry, so we can consider what happens in several cases. So if the size of A is between 0 and 1/2 the size of the entire CFT, you can multiply all of this by pi if you want to, but this is more intuitive. Then what happens is there's effectively no difference between if there is a black hole or if there's not a black hole from the perspective of the homology condition. What this means is that if A is here, the minimal surface, sorry, it's not going to go like that. It's going to go like this, where it feels the effect of the metric, but it doesn't wrap around the black hole. For the mixed state case, and for the pure state case, which I'm going to represent with a dotted line because we don't actually know what's inside that region for a black hole microstate, the metric outside of the event horizon region is the same, so the Ryu-Takayanagi surface subtending A will be the same. And so what you'll end up getting is that this is exactly the same. And so what you'll end up getting here is that S of rho is equal to the weighted sum over S of rho I, which implies that chi is 0. So before you have access to more than half of the conformal field theory, you have no ability to distinguish between any of the rho i's. At leading order, all of this can be corrected by Faulkner-Lukowitz Maldacena corrections. So then what you can see is that after the size of your interval, after you start having more than half the CFT, but still below some critical value, which I'll define in a bit, then what you end up getting is that this region, which I'll try to draw appropriately, now does feel the influence of the homology condition to wrap the black hole. So this will be something like this. But this one, remember, because in this case, the overall state is a pure state, there's still no homology condition, though the metric is still the same. So here, the minimal surface will, instead of going above the black hole, will go below the black hole, because it doesn't have the Lagrangian constraint of the other one, so it's shorter. Yes?
Can you explain what you mean by you have no ability to distinguish the state? What do you mean by that?
I mean that if I trace out on the boundary everything that is not the reduced density matrix on this A region, that means that if I were to look at the relative entropy between rho A in the black hole case and rho A in the microstate case, the relative entropy should be 0 or very close to 0.
But the states themselves are different.
The overall states of the entire system is different, but the point is that if you trace out most of the state, the remaining state that you have access to is not that different.
You mean that for any measurement made in region A, you gain no information about what is the black hole microstate?
That's right.
Oh, so no measurement can tell them apart with any probability. So that would be
That's right. So there's no possibility of distinguishability. Because again, this Holevo information is the upper bound on the accessible information. And it's 0, and this is non-negative. So the accessible information by definition must be 0. Okay, so just to go through, in this case, what you'll end up seeing is that these two lengths are different. This length is longer than this length. So in general, what you'll end up getting is that the Holevo chi will be greater than 0, but will not be equal to SBH. Be less than SBH in this regime. Now, in this last regime, where the Holevo information in this last regime, what you end up getting above L crit, LA, is greater than or equal to L crit. Then in the mixed state case, what you'll end up seeing is that the Ryu-Takayanagi surface actually breaks up into two disconnected surfaces. There will be a piece that looks like this, and then another piece that wraps the black hole. And then in the pure state case, there's no homology condition, so there's no need for the piece that wraps the black hole. The other piece, however, is the same. So in that case, the surface will be this. But then just from arguing by picture, which turns out to be true, these two pieces cancel. So you end up seeing that S of rho minus the weighted sum is equal to the Bekenstein-Hawking entropy again, because you can show that the length of the geodesic that wraps only the black hole is equal to the Bekenstein-Hawking entropy. So here again, you have perfect distinguishability. So note the surprise here. The surprise, there's maybe two different surprises depending on your perspective here. The first surprise maybe is that you don't get perfect distinguishability immediately after you get a little bit more than half of the CFT. If one thought naively from the perspective of the entanglement wedge, one might have thought that as soon as I get more than half the CFT from, in this dotted area, the black hole microstate is now within the entanglement wedge that maybe I can reconstruct from the microstate perspective, so why can't I distinguish them perfectly? That's the first puzzle. The second puzzle is, why do I get perfect distinguishability, if you have a different perspective, of course, why do I get perfect distinguishability before I have access to the entire CFT? So the first question is, why don't I get perfect distinguishability at a half plus epsilon? The second puzzle is, why do I not have perfect distinguishability at 1 minus epsilon? So the reason here can be thought of as, let's see, what's the best way to explain this? So from the perspective of bit threads and of just asking yourself, if I have some reduced density matrix, what does this tell me about? The entanglement wedge is the region from which knowing some portion of the boundary allows me to uniquely reconstruct some region in the bulk. But that means that there may also be regions that are further in the bulk that can influence the entanglement wedge, but that knowing the entanglement wedge does not allow me to uniquely reconstruct. So in particular, we don't necessarily know in the black hole case the specific details in this situation between possible entanglement between a complement in the bulk and the black hole. Like we don't know about the entanglement that's possible like here between the black hole and the complementary region. It's not until that complementary region is in some sense sufficiently far away from the black hole that we have a guarantee that the entanglement is small enough that we don't need that information to be able to reconstruct the details of the specific black hole microstate. So that's the reason why you maybe don't believe this case. For a more technical audience, or if you guys want to ask me later, there's a cleaner way to understand this from the bit threads picture of Matthew Hedrick. The reason why you don't see things here is because the reason why you don't need the entire CFT in order to obtain perfect distinguishability is kind of the same reason. It's the reason that like the correlation between the complementary region and this black hole region becomes very small once the region that you're deleting becomes small enough. So you don't actually need it to be exactly 0 or even particularly close to 0 before you can do it. Yeah, so I guess that's kind of, yeah.
Would you say that, so I would expect that if you increase the size of the black hole, then L crit also increases.
Yeah, one can.
And the limit of the black hole is very large compared to the idea as range, then there should basically be everything.
No, actually, I think the opposite happens. I think that when you allow the black hole to become very large,
Yeah.
I think what actually happens is that L crit becomes very close to 1/2.
Then we should talk about it. I would
Sure. The other thing is that if you take a look at some of the stuff that John has worked on with Uber holography, what you can do is by deleting some portion of this complementary region, you can actually reconstruct the black hole with even significantly less than half of the conformal field theory. The price that you pay is that now you need multiple intervals arranged in kind of special ways. So you don't, it's not that this is that this L crit for one interval is some sort of absolute scale of how much of the boundary region you need in order to do distinguishability. You can do better. Yeah, so I guess this is an example of how thinking about things from a quantum information theoretic perspective can be useful in high energy physics and the question of black hole distinguishability. Thank you.